Hello, in this video we are going to be looking at how do we check whether a binary tree is a symmetric tree or not in JavaScript, and we will also compute the space complexity and time complexity of the solution that we will be building using a recursive approach. Let's first try to get an understanding of what the problem statement is, and then we can jump into the solution aspect of it. So let's say we have a binary tree here with each node having a left node and a right node, and then after a certain depth, when it reaches the depth of the binary tree, we will be having just leaf nodes which won't be having any child nodes further on. So this is depth of 0, 1 and 2. So this binary tree has a depth of 2, and the problem statement states this: if we have a binary tree, we have to see whether it is symmetric, as in the left node, as you can see here, is 2 and the right node is also 2. So at this level it is symmetric. Both nodes have to have same values, and similarly we keep checking further. Now as these two have same values, we have to also make sure that let's say this is the left node and this is the right node of this binary tree, and of this binary tree this is the left node and this is the right node. So in this example this is a symmetric tree. The reason being because the left here is equal to the right node here. So this is my left child node and this is my right child node. In my left child node I saw the value was 2, in my right child node I saw the value was 2, so they were equal. Then I go further and I check the left node of this one has to be equal to the right node of this one. So that means at least partly it is symmetric. Then we check the right node of the left child and the left node of the right child. They also have to be equal. If they are equal, then we can say that this is a symmetric tree. Up to the depth of the binary tree, these conditions have to be met, and that's pretty much the core logic of a solution, and this will translate into code something like this. So I said that I will be having a recursive approach to solve the problem, and I said that I will also check the values of the left nodes and the right nodes, and to do that I need to first have a handler mechanism which will process the left node and the right node. Right now we just get the root, and that's why we need to have a nested function inside. Let's say is symmetric tree, and this will take a left node, let's say P, and a right node, let's say Q, and it will give me a boolean value. So it's going to either give me a true flag or it's going to give me a false flag. And the first thing that we said we are going to do is check left and right values. In this case we receive the root as 1. We check the value, this has value 2, this has value 2. That means it is meeting one of the criterias to be symmetric tree, and then we proceed ahead. So I will just say something like this: if p dot value is equal to q dot value, so p was my left node, q was my right node, then I will say return something. And if they are not matching, that means this can no way be a symmetric tree. So I will just return false here. I will come to this part of the recursive call now. The reason I'm saying this is recursive is because first we just checked, okay, at level 1 we saw, okay, this was the left node value, this was the right node value. Now what? If they are matching, we go to the left binary tree that we have here, and we also go to the right binary tree, and then we check the left of this one has to be equal to the right of this one, because it's basically a mirror reflection. So whatever was on right in the left node will reflect in the mirror here. So this one and this one, they are like a mirror reflection, and they have to be same values. So these two have to be same, and similarly this two which we have also have to be same, and this will translate into code something like this. So after we check the first condition, then we just check p dot left, which is this one, and q dot right, which is this one. They have to match, so this and this have to match, and also we saw this and this, they also have to match, and that basically translates into code as p dot right and q dot left. And this is the recursive part which I mentioned that will help us to reach the solution. So first condition was just check left and right values, then check left binary tree and right binary tree values as well, and that is basically we check 3 matching with 3. So 3 from here has to match 3 from here. So this 2 we have to check. That's our first check which we put here, and the second check is basically this 4 and this 4 that have to match, and both of these have to be true, not only one of them. That's why we put an AND condition here. And this wraps up our logic aspect. Now one thing to remember for recursive functions is that we always need an exit condition, and once you reach the leaf nodes, let's say you reached here at the end, there is no value to compare, and then what do we do? That's why we need exit conditions in the recursive function, otherwise it will just go in a infinite loop. So if p is null, let's say, and q is also null, so once you reach here, you see there is no left node and there is no right node as well, and if both of them are null, that means it's basically a symmetric tree, because there is nothing to check, that is either left value and right value are matching. There are no left and right values. And we need another check condition which will be something like this. So if p is null or if q is null, that means if either one of them is null and not both, that will mean that they are not symmetric values, and that's why we return false in that case. So we put a condition to check for nulls to exit the function, and then we have to also kickstart this recursive function. And the reason we use this recursive function with a left and a right node, because it's not just sufficient to check with the root that we have, and when we trigger it, we will say something like this, and then whatever is returned is going to be the output of this whole asymmetric parent function that we have. And here we will just pass root dot left, which is this one to begin with, and root dot right. That is basically translating into something like this. And that's pretty much it. This wraps up our logic associated with a function. And in terms of time complexity, as you can see, this is a recursive function, and if you have n nodes in the function, it will have to go recursive up to a depth of n, having, let's say, the number of nodes is n, so then it's like going to be getting called recursively n times. That's why the time complexity will be order of n. Now in terms of space complexity, that will also be order of n, because let's say the depth is linear and it keeps on going up to n. In worst case, in best case scenario, it might be just 1 or 2. In that case, it might just be big O of log of n, because it won't increase in such a manner as such that the space complexity basically is based on this recursive calls that we have. So if you just have a depth of 2, it will put in the call stack the values at each depth, which can be like here, as you saw, it made a recursive call here, here, and for each nodes of them. So that's why in that case, if it's step just 2, it will be big O of log of n. But if it, in the worst case, it can be a linear and it can just keep going up to n nodes, the depth, and that's why the space complexity is order of n. Because when we consider space complexity, we consider the worst case complexity when we mention it in the algorithm. And that's pretty much it. Thank you for watching. Please like and subscribe. Bye.